Welcome back to STEM Online Academy. My name is Jason Masterakos. For those of you who don't know me, what the channel is about, we are in advanced mathematics, physics, and just the abstract sciences in general. Channel that specializes in helping undergraduates improve and really strengthen their sixth sense in mathematical intuition, right? Through either concepts, problem solving, and application style of approaches, which makes math much more interesting and alive. Okay, so from last time we were talking about, for those who already follow me, we were talking about um, certain things with Fourier transforms, uh, more more of a geometric approach to Fourier transforms as opposed to computational and algebraic. Okay, which is what I usually do, but I wanted to spend some time looking at it from a geometric lens or a mathematical modeling type of lens. Okay, and Fourier transforms are not as, I mean, definite basic integral is straightforward, the formula, but if you ever get into, you should delve into something called, Fourier analysis. That's more complicated. I'm not going to get into that, and it's not part of what I've talked about in my um, talks. If you followed all of my streams and live shows, okay. All right. So for today, we are going to talk about something called n-dimensional Gaussian integrals. Okay. So, what is that? I'm going to talk about it. It's a concept from my book, Advanced Integration Techniques, where we help help the reader master advanced integrals and applications as well. Okay, so pretty much this book has uh, encapsulated my unique perspective of doing mathematics, as I just mentioned not too long ago, right? All right, so we're going to look at n-dimensional Gaussian integrals. Okay, so that's one of the things, right? And specifically on the menu, right, when it comes to these types of integrals, they're really interesting. Okay. By the way, it helps if you have a background in integral calculus and linear algebra. If you do, then you'll be able to my follow my lectures and streams or live shows or whatever you want to call them, right? But it helps to have a background in these topics. Okay, so number one is why rotational symmetry is the real method for doing these types of problems. Okay. Two, how n-dimensional volume collapses. Okay, so that's another thing that's very important. Three, why Gaussian and power laws produce gamma functions. Okay, so that's number three. Number four, where the factors of pi to the n over 2 and powers of 2 come from. Okay, so pretty much where these factors are produced and pretty much where they come from and how they're incorporated in this in this type of situation, the Gaussian integral. Okay, pi to the n over 2. Number five, why this integral appears everywhere in probability statistics, PDEs, heat flow, C, quantum mechanics, and D, even in machine learning. Okay, so they have applications in that. Okay, so let's look at something interesting here. All right, so the core equation that we want to look at, okay, is the following. Right, this is an integral over the region Rn. Okay, so we have an integral over Rn of the absolute value of x to the alpha, okay, times e to the negative absolute value of x squared dv. Okay, and it turns out it's equal to this jazz here. Okay, all right. So this interesting thing here that I've highlighted, it's equal to pi to the n over 2. So pi to the n over 2. Pi to the n over 2. times 2 to the negative alpha over 2 times gamma of n over 2, all divided by gamma of n minus alpha divided by 2. Okay, valid for when alpha has to be strictly less than n. Okay, so alpha is a power. Okay, n is also a power. They're obviously distinct, otherwise it would say alpha is equal to n. And the gammas just represent the gamma function. Okay, if you don't know about the gamma function, you can either look for resources on it, or you can look at one of my other videos, streams, or live shows on the gamma function. All right, so that's one thing. Okay, so let's look at this integral, right? I know it looks obviously terrifying, right? So the integral looks really terrifying, and that's only because it's written in Cartesian coordinates. Okay, so if you look here, the way it's written, you will agree, anyone will agree that this is in Cartesian, right? Cartesian coordinates, right? So that means x comma y, or x comma y comma z, depending what dimension you're in. All right. So now the moment you switch to some type of symmetry, okay, everything becomes more one-dimensional. Here you can see that we're in n-dimensional space. Right? We have this Rn, right? Rn issue. Okay. So that's one of the things, right? It's going to become easier once we use something called a radial symmetry, right? And then everything becomes one-dimensional. Right? Now, some key things that we need to discuss here. Okay, key conceptual steps I want to talk about with this integral, right? As opposed to just doing the algebra, I think we're just going to look at this conceptually as an interesting conceptual concept. Okay, because the concepts are more important than doing the problems. If you understand the concepts, then everything else flows easily, right? So the concepts and the theory are the most important when it comes to doing any form of math, though, not just this. Okay? So theory and concepts are everything, right? Without that, you just have, like, nothing makes sense. Everything becomes nonsense without it. Okay? So key conceptual steps, right? Number one, okay, number one of the key conceptual steps is that the integrand depends only on the absolute value of x. Okay, so the absolute value of x here, right, as you can see inside of our integral, right? So the absolute value of x, right? So if you look here, this is what tells us. I'm just pausing here. I'm going slowly to make sure you understand. This tells us right here that we have to deal with radial symmetry, right? Or rotational symmetry, quite often called, right? I've written it down as rotational symmetry. So 2, that means we have a rotational symmetry. So automatically, if you have an integral of the absolute value of x raised to some arbitrary exponent, let's say alpha in this case, you have to deal with rotational symmetry. That's good to know, right? Now, number 3, right, is when we have rotational symmetry, we have to use polar coordinates, in other words, known as n-dimensional polar coordinates. Okay? So yes, we're using n-dimensional polar coordinates for this. So if you've seen polar coordinates in your calculus classes, that will be handy. If not, no worries, as long as you understand single variable integral calculus and linear algebra, you can extrapolate it to multiple variables, multiple dimensions, okay? So now you'll notice what I put down here, right, is that, as you can see, we have an integral, right, over dv. So this is over the differential volume, okay? Now the volume splits, right? I'm emphasized here with this red line, okay? This red line here, that the volume splits cleanly. So what that means is, as I said, since we're dealing with a rotational symmetry, this automatically means we have to use polar coordinates. Okay, so polar coordinates like dv is equal to r to the n minus 1 dr d theta. Okay, now some of you might be a little confused. Some of you say, oh, okay, that makes sense, right? Normally in polar coordinates, we take our differential element, dV, dA, doesn't matter what I call it. Usually it's dA, differential element. And we use d theta. That's regular polar coordinates. When it comes to n-dimensional polar coordinates, right? You use n-dimensional polar coordinates when you have to integrate over Rn. Then we use r to the n minus 1 power with dr d theta, where n minus 1 is exponent. Okay. All right, so that's what you need to know, right? When you have an n-dimensional polar coordinates, then you use dv is equal to r to the n minus 1 dr d theta. Okay. Now, there's some things that you need to digest and understand here, right? Is that there is an angular part and a radial part to this dv being r to the n minus 1 dr d theta. Okay. I'll give you a moment to think, try and figure out what is the angular part, right? Which one's the angular part and what's the radial part, okay? Which one's the angular part? This is the angular part. This is all, right? D theta is the differential element in the angle. Dr is the radial part, differential radial part. Okay. So there's an angular part and the radial part to the substitution of the integral that we're going to do, right? Okay. So that's one of the interesting things here. Okay. So we have that. Now, if we go to, I think we should go to the next. Should go to the next page. Okay. Oh, one more thing I want to mention is that the angular part. Okay, so the angular part, I'm going to highlight here, and the radial part. Okay, they give us two different important elements. Okay, one gives a constant. Okay, one gives a constant. Gives a constant. Gives a constant. Okay, so one gives a constant. Okay, so that's the angular part. All right. And the radial part will give you, it just gives the gamma function. This will make more intuitive sense when I show you how to at least break down this integral in one go. It gives a gamma function. But for those of you who love learning mathematics like independently, right? Or you're just an undergraduate student who finds this helpful for your courses, or conceptually, anyways. This type of lecture is something that you may want to revisit. There's a lot of interesting, cool stuff, and it borrows from different areas of math. So there's some linear algebra here. If you notice the type of notation, well, not per se, but very little in the notation. Anyways, gamma function. Okay, so let's go to the next page. All right. So the next page. Okay. Next we have is something interesting here, right? So the way we have to deal with this monstrosity, okay, it is a monstrosity if you look at it. Like, how do you deal with an integral like that? It just looks scary. Okay. Now, as I mentioned, this type of problem, as I said earlier, actually is, well, scary to look at, but once you get to the underpinnings of it, it's pretty straightforward. Okay. Normally they would teach this to you in a master's program. This level of integral they'd expect you to do, right? However, though, I believe that someone who's naturally talented and has a background in integral calculus and linear algebra can handle a problem of this difficulty. Right? Because if you have the prerequisites, you don't have to wait for masters to do it. Right? And that's why I've incorporated these concepts in my book and in my teachings too, when I teach integral calculus, right? By giving people hard problems, um, it really strengthens and prepares them for future endeavors, I believe. Right? So let's go to the next section here, right? Same section, but next page, sorry. So next we're going to look at noticing that the Gaussian, okay, so the Gaussian plus the power equals gamma. Okay, that's my way of breaking this down. Okay, so again, right, we have a Gaussian integral. We know it's a Gaussian integral because it's e to the negative x squared of some sort. Okay, so it's some type of Gaussian, right, over the bell curve e to the negative x squared. But we also have a power as well, x to the alpha. That's a power. Okay. And then this is equal to a gamma function, which it is, right? On the right-hand side, we have a constant times gamma over gamma. So it, right? So this is a good mnemonic or thing to use, that if you have a Gaussian plus a power, you should output some gamma function, okay? Okay, so how do we do this? First off, if we let u equal to negative, not negative, sorry, if we let u equal to r squared, right? So u is equal to r squared, right? I'm just using u substitution, right? Because to integrate, for those of you who know, integrating a problem like this, you would want to use u substitution, okay? Just the way to get the correct differential. So u equals r squared. That means my differential of u is 2r dr, okay? And if I divide by 2 on both sides, again, one half to u equals r dr. So straightforward, right? Now, why did I do u substitution? I noticed a few steps into the future, you can say. It's not quite often it helps to think a few steps ahead to know what technique or method to use. So I noticed by using u substitution, I get this factor of r dr here. Okay, now that r dr, all right, r dr is equal to, that r dr is a factor that comes up in this integral here. Okay, right, so r dr, okay. I think I wrote it down somewhere. Oh, yes, that r dr comes from this integral right here. Okay, so this and this. See, there's a factor of r dr sum. Okay. Now, as you can see, right, we were integrating over r to the n. Okay, r to the n originally of x to the alpha e to the negative x squared dv. But that could have been translated into this. And how do I know this? It translates into this integral. That's because after using n-dimensional polar, right, n-dimensional polar coordinates, which I've highlighted over here, okay, this is the integral that it spits out, right? This is the integral that it spits out. Okay, so that's what we have to integrate. So I've made it from multidimensional to one-dimensional, right? Everything in terms of r. R is changing, everything else is constant, so it's just one variable. All right. Now the next thing is, since we have this integral, right? It's in the form of a gamma function, right? Because if you know what a gamma function is, it's an improper integral 0 to infinity of x to the n minus 1, okay, times e to the negative, right, negative x dx, right? That's what a gamma function is, okay? So if a gamma function, right, is, let me highlight over here, otherwise you're not going to understand what I'm saying. If a gamma function is some variable, let's say r to the whole power of n minus 1, where n here is n plus alpha, that's my n, okay? And e to the times e to the negative x, where x is r squared, okay? Then this would imply that I get a gamma function of n plus alpha over 2. Okay? That should be straightforward, right? Because remember that the gamma of n is equal to the integral from 0 to infinity of x to the n, x to the n e to the negative x dx. Okay, x to the n minus 1. So. It's a nice one. Yes. Okay. So this would imply that our gamma has to be a function of n plus alpha all over 2. Okay. So I hope that is sinking in. I really hope it does. Okay. All right. So why is this important? Why is the final formula inevitable? Okay. Now this formula is inevitable because pi to the n over 2 power, right, implies a certain type of geometry of Rn. Okay, that's just what it does. It implies a certain type of geometry of Rn, and the reason why is because if you're dealing with functions in n, you should be getting something of Rn. Okay, so pi to the n over 2 implies a geometry of Rn. Okay, so that's number one. Number two is powers of 2 implies that you have to have some sort of chains of variables. Okay? So these are really important hints and common misconceptions that students have that I'm putting here, right? Okay, so pi to the n over 2 implies a geometry of Rn. Okay, that's very important. Okay, powers of 2 chain implies a chains of variables, which we did, right? The chains of variables can mean, you know, u substitution, anyways, by parts, polar coordinate, doesn't matter what it is. Some type of chains of variables is necessary. Okay, and then what we have is gamma ratios imply scaling of moments, right? Scaling of moments. Okay, now let's get back to the first page. Okay, I'm going to show you some interesting simulations that are important for you to understand this. And the first one we're going to look at, okay, is a Gaussian blob. Okay, right. So let's go to that. So we're going to look at a Gaussian blob. Okay. Right. And a Gaussian blob, just trying to make sure which simulation it is, goes from 2D to 3D to 5-dimensional space. Okay. And it's going to show radial shells, sorry. Okay. So as you can see here, right, we have something really interesting. We have geometry. This will help you strengthen your geometric intuition, right? As you can see here, we have a Gaussian blob. So think of extrapolating from 2-dimensional space, the left hand of concentric circles there. Okay, those are concentric circles. In 2D Gaussian R2, right? To a 3D Gaussian in R3, to a 5D Gaussian in R5. Okay, right. So that's one thing that is really cool. I wanted to show it to you again, right? So we have a 2-dimensional Gaussian, right, of R2, right, with concentric shells going to becoming a 3-dimensional Gaussian of R3 with concentric cells, and then becoming a 5-dimensional Gaussian of R5. And you notice the pattern here of some R times E to the negative R squared, and then it just continues, right? So again, R squared and E to negative R squared. It could be different factors of R, R1, R2, and R4, right? But it's always R to the n times E to the negative R squared over 2. Okay. All right, so that one is done. Okay, so we've done that one. The next one we're going to be looking at is something called the radial collapse. Okay. So we have an n-dimensional integral here. Okay, so we have n-dimensional integral, which implies implies a one-dimensional radial integral. Okay, so what this is saying is that if we have a shell, right, we have a radial shell, right, with radius r and thickness dr. So I'm getting really into the geometry of the integral here. Okay, is that you have concentric circles, right, of this radial shell. Okay, and it's going to be radially symmetric along the 2-dimensional region, or whatever dimensional region in Rn. Okay, so that is very important to know, right? Is that you're getting an n-dimensional integral, right? and it collapses to a one-dimensional radial integral. Okay, and this is the animation for it. So again, from an n-dimensional integral, okay, and it collapses into a one-dimensional radial type of integral, and you can see the calculations I have and the algebra on the side here of the simulation, showing how we go from chains to polar coordinates, right? From Rn, right? It has to replay again. Sorry about that. Right, so once again, just showing you the entire simulation here. Okay. Everything starts at the origin, obviously, and then radially is symmetric going out. Okay. So again, Rn, right, change to polar or spherical, depending on what the situation is. That's what we did. I showed you a bit of that. And then it will be a double integral using n-dimensional polar coordinates, and then it collapses to a single variable integral afterwards. Okay. And one more simulation, because I always find either geometric shapes or graphs to really help bring math alive and show how it really works. And also, it's also good for applications too, though. All right. So as you can see here, we have something very interesting. We have a parameter slider, right? So what I mean by that is, since our integral depended on some variable alpha, right? So alpha was some parameter, right? It was a parameter slider. And what ends up happening is that we have a mass shift going outwards or inwards, right? And so I showed you uh, from the last slide, the last um, module, the last model, that from a panoramic view, this is more of a well, it is a two-dimensional projection of what's happening, but you can see it behaving in a more interesting manner, right? So as you can see, the radial density here, right, of r to the alpha times e to the negative r squared uh, only affects the shape, okay? Again, that radial density of r to the alpha, right, times e to the negative r squared over 2 is only affecting the shape, okay? So as you can see here, right, obviously the area will either increase or decrease if the shape is getting bigger or smaller, depending, okay? Let's go back to the desktop, and that is pretty much it for today. All right, I hope you guys enjoyed today's stream. Again, I like to, this will be on my YouTube channel, one of the streams. Again, streams are on, uh, let me see the schedule again, uh, Sundays, Sundays and uh, Sundays and Thursdays. Wednesdays is the live show, okay? So live shows are always Wednesday at 8:30, by the way, okay? 8:30 p.m. Eastern. Again, there should be a live show this Wednesday. It is New Year's Eve. Maybe, maybe not. I will try to make it. We'll see what happens. Sometimes things, happen, so I can't always make it. But I'm going to try my best to make it for that day. Okay. And as usual, we're going to be discussing very interesting mathematical topics that apply to the real world, right? Because this is what I'm mainly doing is applied mathematics. Okay, so yeah, making it somewhat more interesting than just doing 100% pure math, which can be a little dry. So, because applied math incorporates, applications, geometric models and stuff like that, and making math more, more hopefully relatable to some degree. Okay, so I'll see you guys Wednesday at 8:30 p.m. Eastern. If not, Happy New Year. If I do make it, then we'll talk about New Year stuff, and also it'll be very light. It'll be a very light day. Okay. Um, but yes, that will probably be it. Uh, But anyways, since this exact reasoning, symmetry first, reduction second, is the backbone, right, of advanced integration techniques, my book. And if you want to master these ideas at a undergraduate to research level, I also mentor undergraduate students one to one who need help. So you can always contact me. The links will be in the description below of the YouTube channel and of this YouTube stream. Okay, and that is it. So again, links will be below in the description. All right. Have a good night, guys. And if I'm not on Wednesday, or if you're not able to make it, Happy New Year. Bye bye.